Hello, ASILOMAR 2021. My name is Alex Berrien. I am a PhD student at the University of Arizona under Department Head and Professor Dr. Tamal Bose. We are here at ASILOMAR presenting our paper titled Adversarial Filters for Secure Modulation Classification. Let's start with an introduction to what modulation is. We have some data, ones and zeros, that we need to map onto a signal S that can be transmitted from point A to point B. So in the figure, we have ones and zeros that go through some form of modulation to produce the signal S, which is sent over a channel through maybe an antenna to Bob, which will receive S. Bob will demodulate this signal to get back the original ones and zeros. And we can see at the top right are some examples of modulation. And different scenarios call for different particular modulation schemes. And the modulation can change during transmission depending on channel conditions or available bandwidth. Depends on the application. Now let's look at modulation classification. We have some samples of a signal S. S is going to be passed into a machine learning algorithm, in this case a neural network. And the neural network is going to tell us what the probability is that some modulation format K is present given the signal S. In this case, 4PAM was the most likely of those modulation formats, so the neural network will pick that as the modulation format. Modulation classification has lots of different applications. For example, in the military, you may want to differentiate between ally and foe by classifying their signals. Or in the case of blind modulation recognition, where you want to identify what the modulation format is without the transmitter Alice telling Bob what the modulation format is. So you can actually save some time and just transmit more data instead of an overhead. And in dynamic spectrum axis, sometimes there may be a busy channel and you get less bandwidth, so you have to use a different modulation format that uses less bandwidth. And there's also the problem of adversarial learning having negative impacts on modulation classification. If we look at the top left is a famous figure from Ian Goodfellow's paper, and we see that a neural network is able to classify this image of a panda on the far left with 57.7% confidence. But if we add this carefully crafted perturbation onto that image of a panda to produce a resulting image that to us humans looks like a panda still, now the neural network thinks that it's a gibbon with 99% confidence. And here's what a gibbon actually looks like on the right. So we can actually fool this neural network by carefully crafting perturbations. And we can do the same thing with modulation classification of signals. We can add some information or signal to another signal to perturb it slightly and fool a neural network. We have an eavesdropper scenario. Alice is talking to Bob and Eve is listening in on their communication. Alice will sample from the modulation format K some signal S, and she will apply an adversarial attack to S to produce an adversarial example S sub A. S sub A is then transmitted over the channel, and Bob will receive that signal. Bob knows that Alice performed some kind of attack, and they have some form of shared key, so Bob can attempt to undo this adversarial attack to get back the original signal as best he can, R hat, and Bob will take this received guessed signal and pass it into his classifier to produce his guess as to what K actually is, K hat sub B. Eve has no idea that there is an adversarial attack going on. So Eve can just take that received signal, R sub A, pass it through her classifier, and she will get what her guess is, K hat sub E. And hopefully, K hat sub E, Eve's guess, will be incorrect, and Bob's guess, K hat sub B, will be correct. Alice has limited transmit power. We're assuming that Bob and Eve have the same channel, so we're just going to say for now that the channel is additive white Gaussian noise and that the transmitted signal undergoes some form of attenuation. Eve's classifier is assumed to be known, and we know that even if we don't know Eve's classifier, there is the property of transferability of adversarial attacks, which just means that if an attack fools one classifier, it can also fool other classifiers out there. And we will also assume that Alice and Bob have a pre-shared key, so no communication overhead, and we're just going to assume that the key was shared securely between Alice and Bob. And we will also assume that there is a minimum SNR requirement that Bob needs to have satisfied in order to be able to decode information. There are two types of attacks that Alice is going to employ in this problem. There is the additive attack, where she just multiplies some perturbation delta by a small real constant epsilon to her signal to produce the adversarial example S sub A. And there is also the filtering attack, which we propose in this paper, which is where Alice will apply an adversarial filter as opposed to an adversarial perturbation to S to get the resulting signal S sub A. In the real world, Bob can't perfectly estimate the channel attenuation. So there's always going to be remnants left of the additive perturbation if Alice employs an additive perturbation. As for filtering attacks, Bob doesn't need to estimate the channel attenuation, so he's good to go. He can just use the inverse filter to get the original signal back. In the simulations on the right, we adjust Alice's transmit power and look at Bob's and Eve's classification accuracy, and we see when Bob gets alpha hat to be 0.9 times alpha, or he's 10% off, his classification accuracy drops off quickly. Or when he even gets it 99% correct, his classification accuracy still drops significantly. Whereas if he gets it perfectly, he's good to go. But again, that's not exactly feasible. A novel method for producing an adversarial filter that we propose in this paper is called the gradient ascent filter, or GAF. The algorithm is as follows. We randomly initialize the seed vector, capital delta, and we use a filter creation function to convert the seed vector into the filter, lowercase delta, that is convolved with S to produce the adversarial example. And then the classifier, H, observes this adversarial example to produce its guess, K hat, of what the modulation format actually is, K. We pass that through some loss function to get the loss, or how incorrect the neural network is. And then we can take the gradient of that loss with respect to capital delta to update the seed vector. And if you train this seed vector for t iterations, eventually you'll end up with an adversarial filter, C of capital delta, which is very good at fooling this classifier. Why can't we just get away with using the seed vector as our filter? Well, the seed vector, during the process of gradient ascent, may end up having some very interesting values in it such that you don't get a stably invertible filter. That's why the filter creation function will convert the seed vector into a filter that has a stable inverse. One approach we have for creating a stably invertible filter is the first tap constrained GAF. So as long as the discrete time for your transform of the filter does not encircle the origin, then its inverse filter will be stable. So what we do is we put the following constraint on our filter delta. As long as the real part of the first tap, delta sub 0, is greater than the sum of all the other magnitudes combined, then the DTFT of the filter won't encircle the origin. And we have the following expression down below to convert any set of complex numbers into a filter that has a stable inverse. If we plot these poles and zeros of the transfer function on the complex plane, as long as all the poles are inside the unit circle, that means that this filter is stable. If we're coming from an FIR filter, which doesn't have any poles, and we invert it, all the zeros are going to turn into poles. So as long as we make sure that this FIR filter has nothing but zeros inside the unit circle, the inverse filter will have poles inside the unit circle, so it will be stable. We've developed an approach for creating filter taps whose zeros are inside the unit circle, while still training our seed vector to full neural network. So what we have is the transfer function of our filter, delta of z, z inverse plus a1, z inverse plus a2, yada yada yada. As long as the magnitude of all these a values is greater than 1, then all the zeros will be inside the unit circle. And then we can expand the polynomial or use Vieta's formula to get our filter taps, lowercase delta 1, lowercase delta 2, yada yada yada, from our a values. So the seed vector can be any set of complex numbers. What we're going to do is we're going to say that delta is equal to delta times beta, and beta can be a number slightly greater than 1, like 1.01, 1.001, capital delta times beta divided by the minimum of all the magnitudes in delta. So this will push all these values outside the unit circle, giving us a, and then we can use Vieta's formula to get our filter taps from all our a values, and now lowercase delta has a stable inverse. We ran some simulations comparing all of our different filters. We did present another filter called the fast gradient filter method, or FGFM, in our paper, but there's not enough time in this presentation to go over that algorithm. So we are simply comparing the first tap constrained graph, the root training graph, and an unconstrained graph where we just use the seed vector as the filter. So the filter creation function is effectively nothing. And in dashed lines, we see Bob's classification accuracy. Ideally, the dashed lines are very high, which is a good thing. And E's classification solid lines will be lower in the classification accuracy curves. And hopefully, E's classification accuracy is always very low. And we will denote the different attacks by color. So black is no attack. When no attack is applied, the classification accuracy is excellent on Bob's end. When the unconstrained graph is applied, the filter created is very good at fooling neural networks. However, it doesn't have a stable inverse. So Bob has no idea what's going on. Eve has no idea what's going on. Nobody's happy. But if we use the first tap constrained graph in green, Eve's classification accuracy is actually quite low, which is good. However, the first tap constrained graph is not very general, so her classification accuracy isn't as low as it could be. And because it has a stable inverse, Bob can easily decode, so his classification accuracy is very good. As for the root training graph, Bob's classification accuracy is also very good in red, the red dashed line. And because the root training graph is more general than the first tap constrained graph, we actually see an even lower classification accuracy at Eve, which is very good. Thank you everyone for watching my video on adversarial filters for secure modulation classification. I hope it was one of the more interesting presentations out of the many. Please, if you have any questions, attend the poster session live or send me an email. Thank you.